Alright, welcome back everybody. In this video we're going to look at Hooke's law and some applications related to the integral based off of Hooke's law. Hooke's law says that the amount of force F that it takes to stretch or compress a spring X length units from its natural length, notice that's a key phrase, from its natural length, is proportional to X. Okay, so the force that's required is entirely dependent on how much we either stretch or compress the spring from its natural length. The number K is a spring constant, and it's a constant that's characteristic of each individual spring. So, thicker springs require more force to stretch or compress than a thinner, lighter gauge spring. Alright, let's look at example 5. We're going to find the work required to compress a spring from its natural length of 1 foot to a length of 0.75 feet if the spring constant is K equals 16 pounds per foot. Okay, so first we'll write our force equation, which, since we know the spring constant, our force equation is just going to be F equals Kx. And now we're talking about a 0.25 foot compression. And we can set up our integral the same way, whether it's a compression or an extension. We're extending or compressing from no extension, the natural length, to, well, in this case, a compression, 0.25 foot compression. And our force function, since K is 16, our force function is F equals 16x. And so if we integrate this, the integral from 0 to 0.25 of 16x, we'll come up with the amount of work that's required to compress the spring that amount. And this is just pure lazy on my part. I really should be integrating something like this by hand. But in fact, it might actually take me longer to type all this stuff in than it would have to integrate this by hand. And we get 0.5, and since we're talking about work here and our units are feet and pounds, it's going to be 0.5 foot-pounds of work that's done to compress the spring from its natural length to a length of 0.75 feet. Alright, example 6. It requires 40 pounds of force to stretch a spring from its natural length of 12 inches to a length of 18 inches. Okay, now I have two choices here. I can either write an equation that's going to be giving me inch-pounds, or I can write it in terms of feet and use foot-pounds instead. I think what we're going to do is write it in feet and use foot-pounds. Find the equation for the amount of force required to stretch the spring x inches beyond its natural length. So we're going to keep x as inches here. Change my mind. Alright, so it requires 40 pounds of force to stretch it 8 inches beyond its natural length. And so our force constant here is going to be 5. And so our equation for the amount of force is going to be F equals 5x. And this is going to be measured in inch-pounds. And then we're going to find the amount of work done to stretch the spring to a length of 18 inches. So we're stretching it from its natural to 6 inches beyond its natural. And there's my integral. And so I'm going to go ahead and integrate. I really don't know why I'm not doing these by hand. It seems kind of silly to take all this time to type stuff in. And we get 90 inch-pounds. Now if I want to convert from inch-pounds to foot-pounds, all I need to do is divide by 12, since there's 12 inches in a foot, and this is 7.5 foot-pounds of work. So either of these would be acceptable here, since we're not guided to answer in either inch-pounds or foot-pounds. Find the work done to stretch the spring to a length of 24 inches. So now we're going to 12 inches beyond natural length. So we're going to integrate from 0 to 12. This function. Why not? Go ahead and integrate this by hand. And we end up with 5 halves times 12 squared, 0 squared. So that's going to be 360 inch-pounds, or 30 foot-pounds of work required. Something you should notice about these units, inch-pounds and foot-pounds, there's a multiplication in there. It's not inches per pound, it's inches times pounds, and feet times pounds in our unit. Alright, going on to example 7. Holy smokes. A spring has a natural length of 1 meter, a 24 Newton weight, extends the spring 0.8 meters. What's the value of K and F of Kx? So our force is 24. To extend it 0.8 meters beyond, so we find that K is equal to 30. And so our equation is F equals 30x for this spring. Part B, use the equation from part A to tell how much a 45 Newton force will stretch the spring. So we take this equation, and the 45 Newton is put in for the force, and we solve for x. So that's going to stretch at 1.5 meters past its natural length. Use the force function from part A to tell how much work will be used extending the spring by 2 meters. So we'll take our force equation and we'll go from natural to 2 meters beyond natural. That's going to be 60. And our units in this case, since we're talking about newtons and meters, the units are going to be Newton meters. And then last part, use the force function from part A to tell how much work will be used extending the spring to a length of 1.5 meters. Same calculation as we just had. And then 1.5 squared is going to be 2.25. 15 times 2.25, that's going to be 33.75, I think. 33.75 Newton meters to extend the spring to that length. Do a double check of my arithmetic here. Alright, cool. Alright, that's the end of this video on using Hooke's law as an integral application. Hope you guys enjoyed it. I hope you guys understand what's going on. And I'll see you next time. Have a great rest of your day.